Welcome back. We will now consider examples on the concepts we have discussed so far by looking at a number of problems on them. So right here we have worked examples, and the first problem here says find the square roots. Find the square roots of the following. So we want to get the square roots of the following complex numbers. So take note of the fact that this has s, which implies that as expected you should have more than one square root. You should have two square roots of the numbers. Okay, so the first one here says a is z equals 1 plus I, and b we have z equals 2. Then we have for c z equals minus 2, and for d we have z equals minus 2i. Right, so we want to get the roots, the square roots of these numbers. So how does this work? We have discussed all of the theories and the processes will follow for us to get the root of these numbers already. These are complex numbers, and what we do firstly is to find r for each of the complex numbers. So for the first part, we're given z equals 1 plus I. So if that is the case, we'll get the modulus of this complex number and get its argument first. So the modulus of this, which will be denoted as r, is equal to the modulus of z, and that will be equal to the root of the real part 1 squared plus the imaginary part 1 squared. So that is obviously the root of 2, right? Then we find the argument of this complex number. Of course, the principal argument, that is the only useful argument, as I've told you separately. So this is the real line, the imaginary line. This is positive, so we have 1. This is also positive, we have 1. So the angle that this, so we locate the points. This is the point that represents a complex number. This is the line from the origin to that point. That should be a straight line, okay, and the angle that makes with the positive x-axis is the argument, so we can call that theta. And with this we are good to go. It's obvious that that is just tan inverse of y over x. So in this case, argument of z equals the tan inverse of y, which is 1, divided by x, that is the real part, which is 1. So that is obviously the tan inverse of 1, which is 45 degrees. So from this, we see that the argument theta is 45 degrees, which is the same as pi over 4 in radians. So know that pi is 180 degrees, pi over 2 is 90 degrees, so pi over 4 is 45 degrees. Okay, so with that, we are good to go. Of course, our calculator could have done this for us directly, as we've shown in the past. Okay, so what do we have to do here? We have to get the square roots of this number. So what you need to recall now is the expression that we obtained for getting nth root of a number in the last few lessons. So you should recall that the nth root of z, which is equal to, in general, when you have z as r into cos theta plus I sine theta, its nth roots are given the nth roots, please, the nth roots of a complex number z in polar form are given by q sub k, as we obtained in the last lesson, equal to r into 1 over n, then into cos. So in this case, we have theta plus 2 pi k divided by n plus I sine theta plus 2 pi k divided by n. So put this here and we state that in this case, k will be varied from k will be equal to 0, 1, 2, and so on and so forth, up to n minus 1. Okay, so this was the results we obtained in the previous lesson. So that means with this we are good to go. What do we just have to identify? We have to identify what our R is. That is the, as we've written here, the modulus of the complex number whose roots are required. N is the position of the root, so to speak, that you want to get. For instance, if it's square root, that means n is equal to 2. If it is cube root, n equal to 3. If it is fourth root, that is n equal to 4. If it is fifth root, that means n equal to 5. So that's how you get your n. It is it tells you the roots that you want to get. Okay, and k will be vary from 0 to n minus 1, so that we obtain all the nth roots of the complex number z. So contextualizing this, we know that therefore, for the problem we have at hand, q sub k, the square root of the given complex number z that we found its modulus and magnitude up there. Then, sorry, let's say its modulus and magnitude. Its modulus and argument up there. So we can now say that thus, therefore, the square roots of the number we're given here, the square root of z, which is 1 plus I, which we have now found its modulus and argument. And by that, if we put it in polar form, it will be equal to r, which is root 2 into cos theta. Theta is pi over 4, so this is cos pi over 4 plus I sine pi over 4. This is the complex number z equals 1 plus I, now in polar form. Okay, so the square root of this will then be given by q sub k, which is equal to r to the power of 1 over n. That is everything we have here. That is root 2 to the power of 1 over 2. Because now we're dealing with square roots, our n is equal to 2. So we're just making the substitution here. So in this case, our r is equal to root 2. So we're putting that here then to the power of 1 over 2. Then we have this right here, which is this will be cos theta. So our theta, that is the argument of the complex number we are taking its root. So theta in this case is pi over 4. So right here we have pi over 4, then plus 2 pi k. We have 2 pi k. Then we divide by n. So our n in this case is 2. So we leave this here. Then plus I sine, so we have this to be I sine theta. So theta is still pi over 4, then plus 2 pi k, then divided by 2. So we close this and close this. So in this case, how will k be varied? We know k should go from 0 to n minus 1. So that means in this case, k will be equal to 0 and 1. We have to stop at n minus 1. Once we have the values provided by k equal to 0 and provided by k equal to 1, we will have the two square roots of the complex number. If it happens that we take other values of n, let's say we take k equals to 2, k equal to 3, yes, they are all acceptable as we've noted in the past, but they will be giving us roots that are already provided by either of these. So that's why these two just gives us these two just give us the distinct roots, so to speak, of the complex number. So with this, we don't have to bother about using any other value of k to obtain the root of the complex number. Okay, so let's go right ahead and see what this gives us now. So we now get it for k equal to 0. So when k equal to 0, we get q0. So that's one of the roots. Okay, will be equal to root 2 to the power of 1 over 2. Then into cos. So for this, when k is 0, we're going to have altogether here, that will be cos of pi over 4 plus 2 pi into 0. Then everything here divided by 2. Then we have plus I sine, we have pi over 4 plus 2 pi into 0. Then everything here divided by 2 again. So we close this off. And what does this give us now? So this is still root 2 to the power of 1 over 2. You can write it as 2 to the power of 1 over 4 anyways. Then into, so we have this to be cos of, so this is pi over 4 plus 0, then divided by 2. So that is pi over 8. So this is cos pi over 8 plus I sine pi over 8. So if we need this to be in scalar form, sorry, in polar form, please, then this is one of our results. Okay, so it is acceptable to leave it in this format. You can also simplify it further. So this is one of the roots of the complex number given z equals 1 plus I. So we can keep that. Then to get the other root, so let's get into it. For us to get the other root, that is when we say k equal to 1. So we can call that q1 and say that will be equal to the root of 2 to the power of 1 over 2. Then we have this to be cos of pi over 4 plus 2 pi k. So this time around we have 2 pi multiplying 1 and this is divided by 2. Then plus I sine. In this case we have pi over 4 plus 2 pi k. So in this case k is equal to 1. Then we divide everything here by 2 and close the bracket. So with that we are good to go. So let's see what the modulus will give us. The argument, I mean, the modulus of this, sorry, remains 1 over 2. Let's see what the argument will give us. This remains root 2 to the power of 1 over 2. So the argument will then be cosine of, so let's tidy this up with our calculator and just get the result directly. So we have this to be pi over 4. So let's see this pi divided by 4. Then we have plus 2 pi. So we have 2 and pi. Then everything here is divided by 2. So let's see what this gives us. So this gives us 9 pi over 8. So that is fine. Let's write that out first. We're getting 9 pi divided by 8. And this is plus I sine 9 pi divided by 8. So that is the second root, okay, of the complex number. Okay, so we can leave the answer this way, but it is not so acceptable. It is not, it doesn't fit our standard because this 9 over 8 is greater than 1, which means that what we have here is greater than pi. And we want our argument to always be between minus pi and pi. We want something that's greater than minus pi but less than or equal to pi. So to take care of that, we note that in this case we can add minus 2 pi, okay, to this result. And if we add minus 2 pi to this result, let's see what that gives us. We know that when we add or subtract 2 pi or multiples of it to an argument, it doesn't change anything there. Okay, so don't mind that we have added or subtracted 2 pi here. You know that we were not adding it to the angle here, we were adding it to the argument we had previously and then dividing everything by 2. So it won't give us the same result as what we had here. Okay, now because we've divided something here by 2 before we added this 2 pi, I mean after we've added this 2 pi. So this time around we just want to standardize these arguments. So we can say this is equal to root 2 to the power of 1 over 2. Then we have the cosine of 9 pi over 8 minus 2 pi. So then we have I sine, we do the same thing here, of course, 9 pi over 8 minus 2 pi. So why am I doing minus 2 pi? Because that's what will make it get back into our range. In this case, it falls above pi. And so if I subtract 2 pi, I know I'm going to get it within the range that's what I'm interested in. If it fell below let's say minus pi for instance, then we would add 2 pi so that it gets back into the range. Okay, so that is that about that. So this is going to give us the roots of 2 to the power of 1 over 2, then multiplying the cosine of, so let's see what this gives us. If we subtract 2 pi from the results we just obtained here, so this answer minus 2 pi minus 2 pi. So let's see what that gives us. So it gives us minus 7 over 8 pi. So this is minus 7 pi over 8. So this will be cosine of minus 7 pi divided by 8. Then plus I multiplying the sine of minus 7 pi divided by 8. And we close this bracket. So with this, we have the second root of the given complex number z equals 1 plus I. So these are the roots, the two roots of the complex number. So the thing is that we have just used 0 and 1 here. Yes, that is all. Now if you substitute 2 for instance, let's say we substitute 2 here, we're going to have this. Let's get back up here. If we made k equal to 2, for instance, let's check what it will be so that you see how that is unnecessary and it is not useful. It won't provide any useful results, okay, at the end of the day. So if we made k equal to 2, for instance, we're going to have this to be 2. Let's put that up again. That will be 2 pi. So we have 2, sorry, pi over 4. So we're going to have shift and then pi divided by 4, then plus. So if we made this 2, this will be 4 pi. So this will be plus. Then we have 4, then shift, and then pi. So at the end of the day, we'll get this to be everything here divided by 2. So this will be 17 pi over 8. This is far, far, far bigger than pi. So we will have to, we know that when we take its cosine, it's going to give us some result, and we could just reduce it so that we have it as a, we have it in terms of the standard, we have it as a standard argument of a complex number. So if I'm going to do that here, 17 over 8 is already 2 whole number, 1 over 8. So basically this is going to be giving us pi over 8, because if we subtract that 2 pi from it as required, it will give us pi over 8. That means it will give us the same result as this. Okay, so that's the point of all of this. So but anyways, we can check. For instance, what will cos pi 17 pi over 8 give us? Let's check for cos 17 pi over 8. So let's say cos of answer, then plus I sine of answer. So this is I, then sine of the answer we just obtained now. Let's give those two and see what they give us. So this is giving us 0.93 something. So 0.923879 blah blah blah. This is 0.3826 blah blah blah. So let's see what that would give us if we actually did cos pi over 8. This is 0.9238, 0.3826. If we did cos pi over 8, you see that it gives us the same result. So cos pi divided by 8, then plus I sine plus I multiplying sine of pi over 8. So we have shifts and then pi, then 8 right here. Then we come here and close the bracket. So this will be giving us the same thing. So let's put in that form. So you see, it gives us exactly the same thing. So if you substitute 2, it's you will just be coming back to this. So you will just have only 2 unique results. If you substitute 3, it will come back to what you had for 1. If you substitute 4, it will come back to what you have for 0. Substitute 5, it will come back to what you have for 1. So and so on and so forth. That is why we just use k from 0 to n minus 1. So it gives us all the distinct roots of the complex number. So these are the roots of the given complex number. Okay, so we have obtained them in polar form, and of course you can obtain them in other forms. Okay, so anyhow you decide to do it is totally okay. And if you are going to obtain them in other forms, now this might become quite complicated because of, for instance, if we get this called cosine of pi over 8, let's see the cosine of pi over 8. I think we can just get back to that. Let's see what cosine of pi over 8 ordinarily will give us. That will be giving us some decimals. So that may be too cumbersome to just capture all together here. But the point is that you can always check if you have done the right thing. So let us enter this complex number that we've obtained here and square it. So let's see if it gives us 1 plus I. So let's get back to that here. So this is plus I into sine of what is that? Sine of the same thing here, which is pi over 8. So we'll put shift and pi, then we'll put 8 here. So let's close up this bracket, and we need to multiply all of this by the root of 2 to the power of 1 over 2. So let's say we have here root 2, then we come out here, then we put this, and we raise this to the power of 1 over 2. Sorry, we don't want to do that. So let's put this as everything here. Let's delete this and put 2. We know root 2 is 2 to the power of 1 over 2 itself, so we can just put everything together as 2 to the power of 1 over 4. 1 over 4 is 0.25, so we can put this here, 0.25. Okay, so then we put the bracket outside. You see why we're doing that shortly. Then we'll come here. We're trying to multiply 2 to the power of 0.25, okay, by everything here. So we'll put a bigger bracket here so that it captures everything we have here as cos theta plus I sine theta. Then we close that big bracket. So we'll just close this bracket. Then for the big bracket that covers everything, we'll put this here. Then we'll raise everything to the power of 2 to see if it gives us z plus I. So we'll raise it to the power of 2. So let's see what it gives us. So it gives us 1 plus I, which is the number we are looking for, its square root. So that confirms for us that indeed this that we have obtained here gives the square root of 1 plus I, because its square is 1 plus I. And if we change this to the other one as well, this one, so we just change the argument. You see all of that things are the same except for the argument part. So this will be giving us minus 7 pi divided by 8. So we just change that to minus 7 pi. So let's see how it goes for that as well. Minus 7 pi divided by 8. So you see it still gives us 1 plus I, even though if we write out the numbers, so if we just wanted to get the actual numbers without squaring them now, so let's remove the square and then just get the actual numbers. So you see this is minus of 1.096 blah blah blah. So let's put it this way, so you can see it is negative of this. So that is right here. By the time you check the other one, we checked it the other time, it wasn't giving us this number. So these are two different numbers, which when squared will give us 1 plus I. So those are the two square roots of 1 plus I. So let's move on and consider the other ones we have here. So we have B, which is equal to Z equal to 2. All right. So we have the square root of 2. How do we get the square root of 2? So your guess is as good as mine. 2 is a real number. The square root of 2 will be plus or minus root 2. Okay, so let us see if our complex number approach here will give us that result. So here we are given that z is equal to 2. Then r, which is equal to the modulus of z, is equal to 2. If you like, this is the same thing as 2 plus 0I. So this is a complex number with 0 imaginary part. So this modulus of this will just be the real part squared plus the imaginary part squared. So that is 2 basically. And for you to get the argument, of course, you can locate this on the argand plane. This is the real line. This is the imaginary line. So the real part is 2. So we have 2 here. The imaginary part is 0. So that is the point that represents this line. And the angle it makes with the positive x-axis is 0. Okay, so that means argument of z here is obviously 0. That means theta is equal to 0. So with that, we are good to go. We want to get the square root of 2. Just following this process strictly. Then we say that therefore the square root. So we're not writing out the formula again. We just want to apply directly. The square root of 2 are given by, that is our z equal to 2 are given by. So going by our expression now, we'll have, so we already have r and theta here. So in this case, we'll have q sub k to be equal to, that will be 2 to the power of 1 over 2, 1 over 2 because we're dealing with square roots, and 2 here because that is the modulus of the complex number z that we're dealing with now. Then we'll put this into bracket and know that this should be equal to, so this should be equal to cos theta, theta is 0 plus 2 pi k, then divided by 2 because n is equal to 2 here, then plus I sine theta, which is 0 plus 2 pi k, okay, then divided by n, which is 2. So we put all of this here. Then we know that our k should be equal to 0 and 1. So we take k equal to 0 and k equal to 1 in terms like that to obtain the two square roots of 2. And for that to happen, we say that k0, the first result will give us 2 to the power of 1 over 2 into, so here we have cosine of, so this will be 0 plus 2 pi into 0, then divided by 2. And this will be plus I sine, we have 0 plus, so that's small, 0 plus 2 pi into 0, then divided by 2 as well. Then we'll close off all of these. So what does this give us? This gives us 2 to the power of 1 over 2 into cos 0. So this is 0 plus 0, that is 0 divided by 2, that is 0, then plus I sine 0. Alright, so this will be our result if we were to put that in polar form. And that is our first root of the complex number. So in polar form, it is this way, it is acceptable. We can also simplify this because I mean this is we can put it in a simpler form. Cosine of 0 is 1, sine of 0 is 0, so we know that means the result here does not have any imaginary part, so the imaginary part is 0. Then the cosine of 0 is 1, so we have here 1 multiplying this, okay, plus 0 multiplying this, so that means what we have is just 1 multiplying 2 to the power of 1 over 2. So that is basically just plus of root 2, okay, positive root 2, or just put 2 to the power of 1 over 2, okay, multiplying 1. So that is one of the roots of the complex number z equals 2. Then that's funny, right? So it looks like what have we really done? This is just root 2. I know the square root of 2 is root 2. Yes. So this is to show you that using the complex number approach, whether it is on a real number or that is a purely real number or otherwise, we know we get this. I will get a correct result. Okay. So let us see what q sub 1 will give us. Then q sub 1 will be equal to 2 to the power of 1 over 2 into, so this time around we'll have cos 0 plus 2 pi multiplying 1, so this will be cosine of 0 plus 2 pi multiplying 1, then divided by n, our n is still 2, then we have plus I sine 0 plus 2 pi multiplying 1, okay, divided by 2. So this is the result from that, and by this we have our results in polar form. We can write this as 2 to the power of 1 over 2 into cosine of, so what do we have here? 2 pi divided by 2, that is pi. So we have the cosine of pi, then plus I sine of pi. So this is I multiplying the sine of pi. So what is the meaning of this? We can leave it this way. We can also interpret this because I mean the form is simple. Cosine of pi, you can check with the calculator anyways, is minus 1, and sine of pi is 0. That's the sine of 180 degrees. That is 0. So this portion becomes 0, this becomes minus 1. So at the end of the day, you have this to be minus of, so this will be negative of 2 to the power of 1 over 2. Okay, so we can keep that as our result. Of course, we know that is minus root 2, if you like, so you can write this as root 2. So this is equal to root 2. This is equal to minus root 2 as expected. So that is that about that. These are the square roots of 2. It gives us plus root 2 and minus root 2. So using this complex number approach gives us very precise results. Okay, it's very precise. So we have here plus root 2 and minus root 2. How do we know it has to be like that? Because we have said precisely that this portion is positive. Okay, even though you can have many results, but we're always going with the positive because this implies the magnitude or modulus of some complex number. Okay, so that is that about that. So the square root of 2 as now revealed by complex number approach are root 2 and minus root 2. So which is fine, which is what we've always known them to be, okay, because those are real numbers. All right, so they are only square roots of 2, and we found the 2 already. So with that, we are good to go. So let's see what the next ones will give us. We have z equal to minus 2. So let's quickly get right into that and see what we get from it. So for the c part, we have z equal to, so we're given this time around that z equal to minus 2. So that means z equal to minus 2, or if you like, minus 2 plus 0i. So with that, you can get r, which is the modulus of the complex number z. So r will be equal to the square root of the real part minus 2 squared plus the imaginary part 0 squared, and with that we're going to get we're going to get 2 squared here, minus 2 squared here is 4, The square root of 4 is to go with the positive root. Okay, and with that, you can get the argument of this complex number. To get that, let's look at the complex number again on the argand plane. This is the real line, this is the imaginary line. On the real line, we have minus 2, so minus 2 should be somewhere here. On the imaginary line, we have 0, so that means it should be on the x-axis. So the line from the x-axis to the from the point of interest to the origin is this. So the angle that this makes with the positive x-axis is going to be 180 degrees or pi. So we know that our theta here is simply 180 degrees or pi, if you like, in radians. Okay, so with that, we are good to go. So that means our given complex number z, which is equal to minus 2, is 2 into cos pi plus I sine pi, of course, unexpected. Okay, so of course we know that this is cosine of pi, again that is minus 1, multiplying this, that will give you minus 2 plus I sine pi. Sine pi is 0, so basically this is the level that this is equal to minus 2. What is the difference between these two? Essentially no difference except that we have put it in a better form that we can operate on, okay, which is the polar form as we have learned so far. So going by this, we now have to get the square roots of minus 2. So let's see what that gives us. So to obtain the square root, so we now say that thus the square roots of z are given by the square roots of z are given by square roots of z are given by the following. So what do we have? We know we need to get q. Okay, so it should be given by q sub k equals r. R now is 2, so we're going to have 2 to the power of 1 over 2. Then we have into cosine of theta. Theta, as we've seen, is pi, so this will be pi plus 2 pi multiplying k, then divided by n. Our n is 2, so this is plus I sine I multiplying sine of pi plus 2 pi multiplying k, then all of this divided by 2. So we close this off and close this off. Okay, so we will now use different values of k here. So we get the first root when q sub 0, that is when k is equal to 0, we have 2 to the power of 1 over 2. Of course, we know here that k should be just 0 and 1 because n is 2. So k should go from 0 to 1 as we have done in previous examples here. So this is going to be 2 to the power 1 over 2 into the cosine of pi plus 2 pi into 0, then all divided by 2, then we have plus I multiplying the sine of pi plus 2 pi into 0, then all divided by 2. So we close this off and close this off. So with that, we can now say this is equal to, so we say q sub 0 is equal to 2 to the power of 1 over 2 into cosine of pi over 2. So we have this to be cosine of pi over 2. This is 0, pi plus 0, so pi over 2 altogether, then plus I multiplying the sine of pi over 2. So what does this tell us and what does this give us? To be precise, this is root 2, obviously, and what we have here is cosine of pi over 2, that is cosine of 90 degrees. Cosine of 90 degrees is 0, so you can check that or verify that with your calculator. And sine of 90 degrees is 1. So basically, this is telling us that our result will be 2 to the power of 1 over 2, which is root 2, then multiplying I, because this portion is 0. So this will be 0 multiplying this plus I, okay, because sine of pi over 2 is 1. I multiplying 2 to the power of 1 over 2. So at the end of the day, you will be getting this to be root 2i. So this is telling us our result is root 2i for this part. So we can keep it like that. So any of these forms can be used to express that first root. Okay, then the second one, that's what we get when q equals 1. So let's get that. That is q sub 1. That will be equal to 2 to the power of 1 over 2 into cosine of pi plus 2 pi. In this case, k is equal to 1, so we put 2 pi multiplying 1, then all divided by 2, then close the big bracket plus I sine. Same thing here, pi plus 2 pi, okay, all divided by 2. So 2 pi multiplying 1, all divided by 2. then we close this bracket. So with that, what do we get? Let's simplify this further. We're going to have 2 to the power of 1 over 2 into the cosine of, so this is pi plus 2 pi, that is 3 pi over 2. So we have here 3 pi divided by 2, then plus I sine. So this is 3 pi divided by 2, then we close this bracket. So can we simplify this further? Is there any need for a further simplification? Obviously, this is 3 pi over 2, so it exceeds pi. So to make it within, to make it fall within our range of the standard values of the argument of a complex number, we can simplify this further. Of course, we know whether or not to simplify this further, it will give us the same result at the end of the day, okay, if we expand it out. But let's simplify this, it makes the work easier, so or it makes our results look better, conforming to the standard. So subtract 2 pi from this, and then we have plus I sine this the same thing, 3 pi over 2. Let's subtract 2 pi from this, and what does that give us? 3 pi, I mean 3 over 2 minus 2, that will be minus 1 over 2. So this is going to be giving us minus of pi over 2. So at the end of the day, we have this to be equal to 2 to the power of 1 over 2 into the cosine of minus pi over 2. So this is minus of pi over 2, then plus I multiplying sine of minus of pi over 2. So put all of this together, and that is our Q1. Okay, so we can just leave it like that. The cosine of minus pi over 2, you can check with the calculator, is cosine of pi over 2, which is cosine of 90, which is 0. Okay, sine of minus pi over 2 is minus of sine of pi over 2. That is minus of sine 90. Sine 90 is 1, so that is minus 1. So what you have here is minus I altogether. Then you multiply it by this, that is going to be minus root 2I. So this is negative root 2, okay, multiplying I. So that is another root of minus 2. So you can see how this approach just fetches all of the roots for us, okay? Once we follow this formula correctly, it gives us all of the roots for the complex number, okay? So life can be just as easy as that when it comes to these numbers. So obviously, if you pick root 2 and square this, it is going to give you 2. If you pick I and square it, it will give you minus 1. So basically, at the end of the day, the square of this is minus 2. And the same thing here, if you pick minus root 2 and square it, it will give you 2. When you square I, it will give you minus 1. So basically, the square of this is also minus 2. That confirms for us that indeed the square roots of minus 2 are root 2i and minus root 2i. So things can be so smooth when we are considering this, and we can do the same thing now for the first question here. Z equals minus 2i. So follow the same process, obtain its modulus and argument first. Having obtained its modulus and arguments, we then make use of this formula again with n equal to 2. Then we have our k again vary from 0 to 1. Okay, so let's get right into it, and that will be the D part of problem 1. So we're given for this D part Z to be equal to 2i. So if Z equals 2i, that is basically 0 plus 2i if you like, and from that we can get our R here to be the modulus of Z, and that is going to be the square root of the real part squared plus the imaginary part squared, and that gives us 2 at the end of the day. And for the arguments of this, we show this on the argand plane. This is the real line, this is the imaginary line. On the real line we have 0, on the imaginary line we have plus 2. So this is going to be plus 2, okay, right here. And on trace, that means that it is located on this imaginary line at this point, because while our x here is 0. So the line from the origin to this point will go this way, and the angle that this makes with the positive x-axis will be pi over 2, or 90 degrees. So theta here is simply pi over 2, quite obviously. So with that, we are good to go. We can now obtain the roots of z equals to I. So we now say thus the root of z equals 2i, which we know now to be 2 into cosine of pi over 2, and plus I multiplying the sine of pi over 2. If you put it in polar form, okay, that is the result. That's the complex number we're given in polar form. So we say the roots, or say the square roots to be precise, please. The square root of the given complex number are, so we get them by using the formula of the q sub k equals r to the power of 1 over n. So in this case, r, that is the modulus of the given complex number, is 2 to the power of 1 over n, that is 1 over 2. Then we have into cosine of theta plus 2 pi k. So theta in this case is pi over 2. So we have pi over 2 plus 2 pi k. Then everything divided by n. Our n here is 2. So put that there and close off this bracket. And this is going to be plus I sine pi over 2 plus 2 pi k. So our k is here. We're not using that yet. And then divided by n. Our n is 2. We close off everything. Then we know that since we are interested in the square roots, since our n is 2, k should go from 0 to n minus 1, which is 1. Okay, so with this, we are good to go. We can now set k equal to 0. So when k equal to 0, we get q sub 0. That is equal to 2 to the power of 1 over 2 into the cosine of pi over 2. So we have this to be pi over 2 plus 2 pi multiplying 0. Then everything here is divided by 2. Then plus I multiplying the sine of pi over 2 plus 2 pi into 0. Then everything here is divided by 2. Again, we close this bracket. And this gives us 2 to the power of 1 over 2 into the cosine of pi over 2 plus 0, then divided by 2, that is pi over 4, so that looks good. That is cosine of pi over 4, then plus I sine of pi over 4. So with this, we are good to go. This will be the first root of z equals 2i. That's what we're looking at, the first square root to be precise, of 2i. And what does this give us? Can we possibly simplify for that? Yes, pi over 4, we know pi is 180 degrees, pi over 2 is 90 degrees, pi over 4 is 45 degrees. So, yeah, if you know cosine of pi over 4, I mean, there is a simple form of that. You know, that is root 2 over 2. And by the time we multiply it by root 2, you know, this is root 2 out there. It is going to be giving us, I mean, root 2 over 2 multiplying root 2. That will be 2 over 2, which is 1 basically. Then our sine of pi over 4 is also root 2 over 2. So this is going to be 1 plus 1i, which is 1 plus I. So this is suggesting that if we squared 1 plus I, we would obtain 2i. So let's see if that is true or something is wrong with our result. So we have 1 then plus I. So let's close all of this. So we have 1 then plus then I, then close these, then square these, and see it gives us 2i. So indeed 1 plus I is a square root of 2i. So this is one of the square roots of 2i. So we can just finalize that this is one of the square roots that we are interested in. So if we wanted it in polar form, this is it. And if we wanted it in the form a plus ib, this is it, okay, or x plus iy if you like. So the next one will be q1. We'll make k equal to 1, then we'll get 2 to the power of 1 over 2 into the cosine of pi over 2 plus 2 pi multiplying 1, then everything here divided by 2. Close off the bracket, then I sine pi over 2 plus 2 pi multiplying 1, then everything here divided by 2. Close this off and close this off. So with that, we are good to go. So what do we get from here? This is going to give us 2 to the power of 1 over 2 into the cosine of this. That is cosine of pi over 2 plus 2 pi. So let's just enter that with our calculator directly. So this is, we have this fraction, this is shift, and then this is pi, this is 2. Then this is plus 2 pi. So we have plus and 2, and then pi. Then we divide these everything here by 2. That gives us 5 pi over 4. So we have cosine of 5 pi over 4. The cosine of 5 pi divided by 4. Then plus I multiplying the sine of 5 pi divided by 4. So we close this bracket. Again, we have 5 over 4 to be something that exceeds pi. Yes, we can use it this way if we just wanted to get our result in the form a plus ib. This is above pi, so we can put the argument in standard form. So if we wanted the result to be in modulus argument form, we wouldn't leave it this way. So we would have to put it so that it falls between minus pi and pi. So for that to happen, this is already exceeding pi, so we can just subtract 2 pi from it. That does not change the value of the results we're getting from this. So this is going to be giving us 2 to the power of 1 over 2 into the cosine of 5 pi over 2. So we have this to be 5 pi over 4, then minus 2 pi, so that it falls within the range of the standard values of the argument of complex numbers. So this is plus I sine 5 pi over 4, then minus 2 pi. So this closes the bracket for us. Then let's see what this gives us. So we'll just subtract 2 pi from the results we have here. Answer, then minus 2 pi. So we have 2 and then we have pi. So that gives us minus 3 pi over 4. So that is the standard arguments. It is minus 3 pi over 4. So this essentially gives us 2 to the power of 1 over 2 into the cosine of minus 3 pi divided by 4, then plus I multiplying the sine of minus 3 pi divided by 4. So that is our second root, okay, Q1. And with this, we are good to go. What does this give us now? We can leave it this way. As a matter of fact, we could have left it this way because essentially cosine of 5 pi over 4 will give us the same thing as this. Sine of 5 pi over 4 will give us the same thing as this. So we could have it this way as well. The only issue with this is that the argument would not fall within range of minus pi to pi. So but anyways, if you express the final result this way, it is acceptable, it is correct. Okay, but this is a standard way to actually put this in polar form, put this complex number in polar form. All right, so with this, we are good to go. We might want to check out if this can actually give us simple algebraic result or form. So maybe it will be in sort form, or to just give us actual integers so that we can just write out the results directly like that. So let's see what cosine of this answer will be. So let's say cosine of the answer we just obtained now plus I multiplying the sine of the same answer. Let's see if it's giving us that. So this is root 2 minus root 2 over 2, then minus root 2 over 2. So we know 2 to the power of 1 over 2 itself is root 2. So when we multiply this by root 2, we'll be getting 2 over 2, which is 1. This also will be getting 2 over 2, which is 1. So this is minus 1 minus I. So right here, this tells us that the second root is minus 1 minus I, which is expected because that will be the negative of the first square root. And if we put the negative out, we know it will be giving us the same results when we square. Okay, so this is the negative of the first square root that we obtained up there, okay, which is correct and which we can verify by checking with our calculator that minus 1 minus I when squared. So we say when minus 1 minus I, close off the bracket and square this, it gives us 2I, okay, as expected. So we now have the square root of 2I as well. So those are the two square roots of 2I. So with that, we are done with the first problem here. Let us have another example before we end this lesson. So let's have an additional page and take on another question before we end this lesson. So that's all for question 1 or problem 1 if you like. So what we have here is find the fourth roots find the fourth roots of root 3 plus I, root 3 plus I. So let us get all the fourth roots of root 3 plus I. So in this case, this should be quite easy as well. We know the process, so we just get right into this. We get the modulus and argument of the given complex number first. So this time around, we're given z equals root 3 plus I. So with that, root 3 plus I, we can get the modulus argument. So this is going to give us R in this case will be equal to the modulus of Z, and that will be equal to the square root of the real part, root 3 squared, plus the imaginary part, 1 squared. Root 3 squared is 3, 1 squared is 1. So altogether here we have 4. So root of 4 is 2. So the modulus of this is 2. Okay. So we are good to go with that. Then the next thing is to get the arguments of these, and the best way to do that is locate these on the argand plane. This is the real line, this is the imaginary line. So for the real line, we have the coordinates will be root 3, so that is positive root 3. We have on the imaginary line, we have positive 1. So at the end of the day, this will be located here. The complex number is located here. The line from that from the origin to that point is this, and the angle that this makes with this is theta. So obviously that is positive, and it will be given by the tan inverse of y over x. Okay, so right here the argument of the given complex number z is simply equal to the tan inverse of y, which is 1, divided by z, sorry, x, which is root 3. So with this, we can get our angle theta, which is the argument of the complex number. So let's see what that tells us. That should be 30 degrees or 60 degrees, I don't know. So this is tan inverse of 1 divided by root 3. So we have 1 divided by the root of 3. We close this off, and say this is pi over 6. Okay, so that's 30 degrees. Okay, so we have theta to be equal to pi over 6. So it's as easy as that. Now, this time around, we want to get the nth roots. Okay, the fourth root. That means our n is equal to 4 in this case. So we now say that thus the fourth root, so in this case, we know n is equal to 4. Okay, of z, the number we're given, which is root 3 plus I, which we have now seen that in polar form, it will be equal to 2 into cosine of theta, which is pi over 6. So this is cosine of pi over 6, cosine of pi over 6 plus I multiplying the sine of pi over 6, okay, are given by this expression. So let's write out the general formula yet again. So we know that this should be q, so a q sub k into r to the power of 1 over n. So this is r to the power of 1 over n. Then it should be cosine of theta plus 2 pi k, so divided by n, plus I multiplying the sine of theta plus 2 pi k, then all of these divided by n, then we close off the bracket, and then we know that k should go from 0 to n minus 1. So this is 0, 1, 2, and so on and so forth up to n minus 1. So we can now contextualize this. Okay, so in this case, then we know our r is 2 and our theta is pi over 6. So we just contextualize that. That means that for this case, q sub k will be equal to r to the power of 1 over 4, and this will be equal to the cosine of theta. Theta is pi over 6 plus 2 pi k, so we'll come back to use k later, then all divided by 2. Sorry, n is equal to 4, please. So this is divided by 4. Then we have plus I multiplying the sine of theta, which is still pi over 6, then plus 2 pi k, then all of this divided by 4. Then we close this bracket and close this bracket. Of course, we know that k should go from, in this case, 0 to n minus 1 will be 0, 1, 2, and 3. So this will give us all the four results, all the four roots, all the four fourth roots of the given complex number. Okay, so with this we are good to go. We just use the values of k like that from 0 to 1 to 2 to 3, and we get all of the fourth roots, okay, of the given complex number. So therefore the fourth roots, that will be given by 0, k0, k equal to 0. So this will be r, r in this case. So we also substitute r here, please. We got r up there to be 2. Okay, the modulus of the complex number is 2, so we have to have used that here. So this is 2 to the power of 1 over 4. So what we have here is 2 to the power of 1 over 4. Then we have the cosine of pi over 6 plus, so let's shift this up a bit. So this is pi over 6 plus 2 pi into 0. Then everything here divided by 4. Then we have plus I multiplying the sign of pi over 6 plus 2 pi into 0. Then everything here divided by 4. So we close this off and close this off. With that, now obtain this to be equal to 2 to the power of 1 over 4 multiplying the cosine of, so this is pi over 6 plus 0, then divided by 4, that is pi divided by 24, and this is going to be plus I sine pi divided by 24. So that is that about that for q sub 0 in polar form. So in polar form, it is exactly this that we get. And if we want to have this in the form a plus ib, let's see if it gives us whole numbers or it gives us sort. So we just write it out. If it doesn't, we can just ignore it and just leave it this way. Okay. Um, so we have this to be cosine of pi divided by 24. So this is pi, and then this is divided by 24. Then we close this, come here and close this. This is 0.999 something. Okay, so that is a lot of headache. There's no space to write that out. So let's leave it this way. Of course, we can verify that this is correct in that when we raise everything here to the power of 4, it must give us the number we started out with, which is root 3 minus I. Okay, so that's a way to verify our results. We can let's do that when we're done with everything. Okay, we'll come back to do that because when we're done with everything, of course, the differences will just be in the argument, so it'll be easy to verify them all together at once. Okay, so let's get ahead with q sub 1. So it will follow that q sub 1, in this case, we are substituting k equal to 1. This will be equal to 2 to the power of 1 over 4 into the cosine of, so this is the cosine of pi over 6, then plus 2 pi multiplying 1, then we have all of this divided by 4. So this will give us this here and this here, then plus I multiplying sine, then we have pi over 6 plus 2 pi multiplying 1, then all of this divided by 4. So we close this off and close this off. So what does that amount to? We have pi over 6 plus 2 pi, then we're dividing everything by 4. So let's use our calculator for that. We have pi over 6 pi divided by 6, then plus 2 pi, 2 multiplying pi, then all of this divided by 4. So this is giving us 13 pi divided by 24. 13 pi divided by 24 is less than 1, so that is within range. Okay, so we just leave it like that, 13 pi over 24. So then our q1 is equal to 2 to the power of 1 over 4 into the cosine of 13 pi divided by 24, then plus I sine of 13 pi divided by 24. So put all of these together and that gives us another fourth root of the complex number. So let us keep this like that. Then we'll move to the next one to get our Q2. Q2, that means our K will be equal to 2 here. That will be 2 to the power of 1 over 4 into the cosine of, so we're substituting K equal to 2. Instead of K equal to 0 and 0, K equal to 1 that we have used so far. So we come here again and substitute K equal to 2 this time around. So this will be giving us something like cosine of pi over 6, right? Pi over 6, then plus 2 pi this time around into 2, then everything here is divided by 4. So we close this off and we have plus I multiplying the sine of 2 pi multiplying 2 divided by, sorry, pi over 6, then plus 2 pi multiplying 2, everything here divided by 4. So this and this is closed off. Okay, so with that, We are good to go. Let's see what this gives us by the time we insert all of this here. We have pi over 6 plus 2 pi. So this time around, this is 2 pi multiplying 2. So this will become 4 pi. So we have this to be 4 pi. So this is 25 pi over 24. So 25 over 24 is greater than 1. So this is greater than pi. It is out of range. But let's write it. Let us write out this result first. Okay, so this is 25 over 24. So this is going to be 2 to the power of 1 over 4. Then multiplying the cosine of pi over 6. Sorry, 25 pi over 24. 25 pi divided by 24. Then plus I multiplying the sine of 25 pi divided by 24. So we close this and we close this, and that is for this part. Yes, the answer can be left this way, but no, we want this argument. That is, if we are going to say this is a modulus argument from, or say the polar form is of the complex number, then we should have this as a standard argument. So I have this as a standard argument. We know that it is now exceeding pi, so we want it to be within pi and minus pi. So we can subtract 2 pi from this result. Okay, so let's go right ahead and subtract 2 pi from this. This will be 2 to the power of 1 over 4. Then multiplying the cosine of 25 pi divided by 24 minus 2 pi, then plus I multiplying the sine of 25 pi divided by 24, then minus 2 pi. So we close that off and close that off. So what do we get from this? So we just do minus 2 pi of this result we just obtained, and that is giving us minus 23 over 24 pi. Minus 23 over 24 pi. Okay, minus 23 over 24 pi. So that is less than minus pi. So that works fine for us. So that is our Q3 equals 2 to the power of 1 over 4 into the cosine of minus 23 over, that's minus 23 pi over 24, then plus I sine of minus 23 pi over 24. So we're good in modulus, in polar form. That will be our, this is Q2, please. So that will be our third result, okay, for the fourth root of root 3 plus I as given in the problem statement. Okay, then we have to get the fourth one now. Okay, this is the second result, this is the first one, this is the second one, this is the third one. We know we should have fourth roots of a complex number. Okay, so we now get q sub 3. Substituting now k equal to 3, then we have q sub 3 will be equal to 2 to the power of 1 over 4 into the cosine of, so what are we doing again? Here we're using k equal to 3. So this is the expression, the general expression for the roots. So this time around we're substituting k equals 4. So let's go right there. So this will be pi over 6, okay, plus 2 pi multiplying 3, k equal to 3, please. So then divided by 4, then plus I sine, this is pi over 6, then plus 2 pi into 3, then everything here divided by 4. We close off the bracket and close this off as well. So let's see what this gives us. When we use our calculator, we can do that directly with our calculator. This is going to be pi over 6. So we have pi divided by 6, then plus, so this time around we have 2 pi multiplying 3, that's a 6 pi. So we have 6 plus pi. Then we divide everything here by 4, so that gives us 37 pi over 24. That is still greater than pi, but we'll come back to simplify that. 37 divided by 24 pi. So this is going to be equal to 2 to the power of 1 over 4, then multiplying the cosine of pi over 6 plus, so this is 37 pi divided by 24, right? 37 divided by 24, yes, pi. So with that, we are good to go. We can say this is plus I sine, then this is 37 pi divided by 24, then we close this bracket. So to make this a standard argument, we say this is 2 to the power of 1 over 4 into the cosine of 37 pi divided by 24, then minus of 2 pi. So we close this up and say this is plus I multiplying the sine of 37 pi divided by 24 minus 2 pi. Just to ensure that our argument here, okay, is standard. That is, it lies between minus pi and pi, okay, as required. So this is going to be giving us 2 to the power of 1 over 4 then into, so let's see what this gives us, 37 pi divided by 24 then minus 2 pi. So the answer will last obtained minus 2 pi as minus 11 over 24 pi. So it is now within range. So this is going to be the cosine of minus 11 over 24 multiplying pi then plus I sine minus 11 over 24 multiplying pi. So this closes off, and this will be the fourth of the roots that we're interested in. The fourth root of z equals root 3 plus I. So with this, we are good to go. So we now have our result. We should verify our results with our calculator. Don't forget that this process of getting the modulus and the argument of the complex number can be completed with the calculator directly. If you didn't need to show how you came about that, you would just use the calculator here for this. So this is root 3 plus I, for instance, root 3 plus I, and then you can put this, once the calculator has to be in complex mode, of course, you can come here and then put it in the form R and theta, so you can put this here and say what that is. So it tells you that the modulus is 2 as we have obtained, and the argument is pi over 6. So this could have been sorted directly like that with the calculator. Okay, I've shown it here because I want to show you how everything works as we've been doing so far. So we just use the calculator now to verify this. Okay, so let's see how this plays out, and that is going to be the, so let's enter this function. Let's enter for the first one and see. But that means that when we put all of this together and we raise everything to the power of 4, it must give us root 3 plus I. That we are getting its fourth roots. Okay, that is how we verify our results. So we can do that right away. Let's put a bracket here, and then we'll put 2 to the power of 1 over 4, that's 0.25. We can write 0.25 directly. Then we're multiplying by the cosine of this. So this is cosine of pi divided by 24. So we have pi here and then we have 24. Then we come out of that bracket, close it. Then we have plus I. So this is how to enter I. Then multiplying sine of the same argument, pi divided by 24, pi here, and then divided by 24. Then we come out here and close this bracket. We close the second bracket here there as well. Then we close the last bracket. Then we raise everything here to the power of 4. So let's see what that gives us. So it's giving us error in the sense that this calculator cannot raise all of this to the power of 4 directly. So that is a lot of problems. That is a lot of problems because of that. So let's see if it can square this. Yes, it can square it. So having squared this, we want to square the answer. We want to be able to get back to what we have there. We won't be able to get back to what we have there. Let's see, can we keep these results? So this is what we have just obtained. I want to see an efficient way or an effective way to just square all of these. Let's see if it works. If we go back up there, sorry, so let's say this is off and then we'll replay. Okay, replay. So yeah, so let's see if we can repeat this thing here just beside it, and it will give us the result that we want. So this is 2 to the power of 1 over 4. So let's say 2 to the power of 0.25. And then we have the cosine. Sorry, let's get back down first. So this is multiplying the cosine of cosine of pi over 24. So we have shift and then we have pi, then divided by 24. So we're just trying to find our way around the limited capacity of this calculator to just raise a number to the power of 4. Okay, so when you raise it to the power of 2 twice, then multiply the 2. Okay, I think it should work. So let's see if it works anyways. And then this is going to be sine I multiplying sine of pi over 24. So that's a shift, and then we have pi. Then we divide this by 24. Then this is closing off here. Then close off the big bracket before, that's the big bracket after this. Okay, then close off another bracket, then square this. Let's see if it works. So it gives us 1.732. Yes, 1.732 is actually the root of 3. Okay, root 3 is 1.732, blah blah blah. So that is correct. Plus I, we know this is meant to be root 3 plus I, so it gives us precisely that. So that confirms that this result that we've obtained here is correct. So we can confirm the others. What we just need to do is to go back and change those arguments up there. So we just change this argument. So this one is 13 pi over 24. So we just make this 13. We have a lot of them to do. So let's go to the next one. 13. Okay. Then go to the next one as well. Change that to 13. So this will give us this, which is 13. And we go to the next one. That is 13. Okay, let's see how that works. That is 13. Why is it giving us this? Okay, so that's 13 pi. Then, okay, I guess that's all for the second part as well. Cosine of 13 pi, 13 pi, 13 pi. So we're good. So that's captured everything for us. Let's see what this gives us. So it gives us the same thing again. 1.732 blah 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 plus I. Okay, so that confirms that this result is correct. And for the third one, minus 23 in place of 13. So let's get back to this and use minus 23 in place of 13. So let's delete these and delete these. Sorry. So this is 3 pi divided by 24. 3 pi divided by 24. Yep, we want to move these up. We want to put in minus and 13. Yep, minus 23, please. Minus 23, so this is 2 and 3. Minus 23 pi over 24. Yep. So move to the next one. Minus 23. So let's move this here, delete this. So we have minus and 2, so that makes it minus 23. Then we move to the next one. And we can change these as well, delete these, minus and 2, so that makes it minus 23. So we're good, minus 23. Yep. Then the last part here, we'll change that to let's change this, delete, and then we'll put minus and 2. Yep, so we're good. And that is giving us what would this give us? We get our result here to be 1.732 blah blah blah. Okay, that is good. That works fine as well. Confirmed. Then the last part also, we put minus 11 over 24. That is, instead of using this minus 23, now we now have minus 11. So we can get back to this and confirm that for ourselves as well. So we're deleting these minus 11 this time around. So this is also minus 11. So delete, put in 11. Then the next one, we have minus 11 as well. So this goes here. We have delete, and then put 11. Then go to the next one to be sure there's pi there. Let's check carefully. Okay, yeah, so there's pi there. Then we have this also. We place that here and delete, then we put 11. So that's minus 11. So I guess we're done with that. So let's check. So this is also root 3 plus I. And that is that about that. Now, before we end this lesson, I want you to pay attention to something. Now, we've seen that indeed, if we try to look at this now, if we try to get the square roots, okay, with our calculator directly. Let's say that our calculator is a complex mode and we wanted to get the square root of minus 2i. Let's check what might happen. If we want to get the square root of minus 2 multiplying I, so let's see what it gives us. It gives us error. So calculator cannot do that, even though it is in complex mode. Okay, it cannot do that directly. But we know we want to get the square root of minus 2i. So we can try out something here. Let's see if it works out for us. We know that the number we're looking for is the square root. So let's say q is a square root of this. That means q is equal to the root of z, which is the root of minus 2i. So we can say q is equal to the root of minus 2i. Then if we square this, we will have q squared to be equal to minus 2i. And by that, we can say q squared plus 2i equals 0. Okay, this is going to be some quadratic equation. So let's see if we can solve this quadratic equation and obtain its roots. It will give us two roots, it will give us two results. Okay, so if we put this in standard form, this is q squared plus 0q, then plus 2i. Okay, everything is equal to 0. So if we solve this quadratic equation, we know its roots are going to be the square root of minus 2i. So let's check if our calculator will be able to do that. If it's able to do that, then it should produce the two square root that we are interested in. Um, so for that to happen, let's see how it goes. Let's put this in equation mode. Then ax squared plus bx plus c, that's its square root, and that's its quadratic equation. So let's see if it's going to work out for us. Then it asks us for a, that's the coefficient of the square term, that is 1. The coefficient of the linear term, that is 0, and then the constant, that is 2i. So let's see if it can work for us. So we cannot use 2i, you cannot enter, oh my god. So let's say we have 2 into the root of minus 1. Let's see if it works for us. So it gives us error. So if your calculator is able to deal with this directly, then you are good to go. So it cannot work with this because it has this complex coefficients. However, for a problem like this, for this C part, it should be able to help. So that means that in place of this 2i or minus 2i, we have minus 2. So if we add minus 2, then this will be 2, and then this will be 2. So let's see if it solves that for us. So in that case, we have 1 for that part, we have 0, and then for the last part, we have 2. So let's get rid of all of this and see what it gives us if we enter 2 right there. So the third part is 2. So let's see what the answer is. So it gives us minus root 2i. It gives us root 2i and minus root 2i, which is correct, which is precisely what we obtained down here when we got the roots of minus 2. Okay, when we got the root of minus 2, you should remember we got root 2i and minus root 2i. So that works perfectly. So if you want to get, let's say you want to get cube roots of a real number, maybe it's a positive real number or negative real number, or you want to get the square root of a real number, the calculator can help in that sense. So you make it a cubic equation or a quadratic equation, then you use the calculator directly. It cannot help for this case, or let me say I haven't seen any way that the calculator can help with that. In case you know it anyways, you can share with me in the chat room. Okay, but for this, we say that we have, so that's all for this one. So we've confirmed that. So let's say, for instance, that I was interested in the cube roots of, let's say, 8, or the cube root of minus 8. So if I wanted to get the cube root of minus 8, I could say, okay, I'm interested in, okay, that means our complex number is minus 8. Now I'm interested in the cube roots of minus 8. I know minus 2 is a cube root of minus 8. But for cube root, I should have three answers. So what would I do? I know q, I would say let q be equal to a cube root of minus 8. And that means if I raise this to the power of 3, q to the power of 3 will be equal to minus 8. That means q to the power of 3 plus 8 will be equal to 0. So I can form a cubic equation from this because I know my calculator can solve a cubic equation. So I can say this is q cube plus 0 q squared plus 0 cube, then plus 8 equals 0. So let's see if our calculator can give us three solutions to that, okay, including the complex roots, okay. So for that, we are going to go to put our calculator in equation mode. This is for cubic equation, so we choose 4. And for the coefficients, for the first term we have 1, the second we have 0, the third we have 0, and the third or the fourth we have 8. So let's see if it works for this. It gives us minus 2, it gives us 1 plus root 3i, and it gives us 1 minus root 3i. So those are the three cube roots of 8. So you can make the calculator work that out for you. So that tells you that we are dealing with square root and also cube roots. Your calculator can help out directly this way if you are getting it for a real number, that is a purely real complex number, okay? That is a complex number that doesn't have an imaginary part, because this calculator entertains the use of complex terms like that, okay? So let us try out something else. So that is the idea. Those are the cube roots of minus 8. The three of them, it gives you the 3 like that. So let's go back to complex mode. Let's try out something else. We had this the other time. I just thought of something I want to try it out. So we have this the other time to be q squared. We said if you want to get the square root of this, it means we have q squared to be equal to minus 2i, which means that q squared plus 2i will be equal to 0. So q squared plus 2i equals 0. Let's see if our calculator can solve that. There's another way we can solve an equation here. So for that, let's use shift and then enter x. Okay, sorry. Let us enter x in place of q, then x squared, then plus 2i. So this is plus 2, then i. Then we can now say, let us solve this. So this is solve on this here. So we can press shift and then this, and it doesn't solve that. It doesn't work. We cannot solve this for us. So the calc will not work as well. So let's calculate this first. It just given us that. So you cannot do the solving for this, so we have complex coefficients. So that is the limits of our calculator. But as you can see now, if you want to get the cube root of a purely real number or the square roots of a purely real number, and you want to get all of the answers, just put it as an equation, maybe a quadratic equation or a cubic equation in this form, and you're good to go. And if it happens that luckily you have at your end a scientific calculator that can solve an equation into the first power, then that is extremely good and better than what we have here. Then that means that in that case, for even this second problem we solved, you could have obtained the result directly with your calculator. That means you just need to form that equation, then you have something like q to the power of 4. So for this last part, it will just be q to the power of 4 um, root 3, then minus I equals 0. That is if it can take in complex coefficient. If it cannot, then you cannot do that here. Anyways, know the standard process, know the standard procedure as we have presented it here. That is most important. And know when, if you are not required to show how you came about the result, when you can take advantage of the calculator if you want to get the square root of a purely real number, or you want to get the cube roots of a purely real number. And that is all for this lesson. So I'll see you in the next lesson as we consider the nth roots of unity, some characteristics of the nth roots of unity, before we take more examples in this chapter. Thank you for watching.